Okay friends, today we will discuss the introduction to microprocessor Intel 8085. Let us first try and understand what are the basics in it. Well, Intel 8085 is an 8-bit microprocessor which was first built on NMOS platform. Now, we all know NMOS platform means it's N-type metal oxide semiconductor. It was first packed in a dual line package. DIL is dual inline package, which was having 40 pins, and it was fabricated using large scale integration technique. Well, 8085 basically works on a single power supply, and the maximum voltage that we can apply to it is plus 5 volt DC. The clock speed is around 3 megahertz. Therefore, if we try to find out the clock cycle, it comes out to be 320 nanoseconds. Well, the microprocessor is basically having 80 instructions, and there are 246 operational codes. Along with that, we also have 10 more hidden operational codes which we will discuss later. Those 10 instructions were not released by Intel. Let us now try to see the pin configuration of Intel microprocessor 8085. Every microprocessor is made up of combinational and sequential circuits, and whenever we have sequential circuits, those circuits actually work as per the instruction set along with the clocks. So without clock, sequential circuits will never perform. So there is an internal voltage control oscillator inside the microprocessor 8085. Only thing that is required is a crystal. A crystal of 6 megahertz is being connected between X1 and X2 terminal. Well, the 8085 can address up to 16 bits. So 2 to the power 16 is roughly around 64 kilo locations. So a microprocessor 8085 can actually address 64 kilo locations of a memory. The address bus is broken down into two halves. One is the upper address bus and the other one is lower address bus. But in 8085, the lower order address bus is time multiplexed with data bus. We will discuss how this bus can be utilized as address and data bus using demultiplexing technique. There are few pins such as ready, reset in, reset out and clock out. We'll discuss this later on. There are certain status and control signals. Among them are ALE, which is address latch enable, IOM bar, S1 and S0 are status signals. This indicates whether a microprocessor is presently communicating with IO, that is input output device, or the memory. There is S1 and S0. The combination of S1 and S0 tells us whether a microprocessor is in read state or it is in the write mode. There are two more control signals. One is RD, that is read, another is write. Here we can see both are bubbled. That means when this particular terminal goes low, we can say that the microprocessor is presently in the read mode, and if this is low, we can say that the microprocessor is in the write mode. There are few more pins. Among them are interrupts. We will discuss each and every pin later on. There are two more pins. One is SID, another in SOD. SID is serial input data, and SOD is serial output data. There are two more pins. We call them hold and HLDA, that is hold acknowledge. These are basically used for DMA operations. Okay, we will classify those various signals basically into 6 groups. The groups would be address bus, data bus, control signal and status signals, power supply and frequency signals, externally initiated signals, serial I/O ports. So we will be basically classifying these various signals into these 6 groups. Okay, now let's take up address bus. Now, as we know that the address bus is 16-bit, hence the total capacity of addressing is around 2 to the power 16, which is 64 kilo locations of memory. So a microprocessor, if a memory has to be connected to Intel 8085, it should be having 8-bit word size and around 16 address bits. So a total of 64,000 locations of that memory can be accessed through 8085. Well, the address bus is presently being split into 2. One is called the upper address bus, that is pin number A15 to A8, and lower time multiplex address bus, which purpose dual purpose, one as address, another as data bus, and we will designate this as AD7 to AD0. Well, the upper address bus, that is A15 to A8, is unidirectional in nature, and the signal always comes out of the MPU 8085 to the external devices. It can be an I/O device, it can also be a memory device. But the lower order address bus is time multiplexed with data bus, hence it serves dual purpose. It can also carry address, it can also carry data, but since it is time multiplexed, if we at all want to use this bus, we will have to demultiplex it, and demultiplexing is carried out using demultiplexers and a signal called ALE. Now let's see the multiplex lower order address bus. This was first introduced in 8085 to accommodate some terminals which are now known as interrupts. 8080 and 8085 are similar, but 8085 is advancement over 8080. 8080 microprocessor didn't have any provisions for interrupts. To accommodate those pins, the lower order address bus, that is A7 to A0, was multiplexed with data bus, and those 8 pins which were released were used as interrupts in 8085. Okay, these 8-bit bus serves dual purpose. One can be used as addressing, other one can be used as carrying data both from in and out of the MPU 8085. Now, to fetch instruction, that is the operational codes or operands from the memory, the MPU needs to generate a 16-bit address. Since the upper address bus A15 to A8 is dedicated for addressing, the signal only comes out of those address bus. But since the lower order address bus is time multiplexed, we need to demultiplex that bus so that on the first cycle or on the first time t state of a machine cycle, the addressing is done through those 8-bit bus, and on the later half data can enter into the microprocessor through the same bus as data bus. This can be carried out, the demultiplexing can be carried out using a latch and a signal that comes out from address from ALE, which is otherwise known as address latch enable. We will take up the demultiplexing portion in the next lectures. Well, now if we talk about control signal and status signal, we have ALE. As we have already learned why ALE is used. ALE is nothing but a positive going pulse generated each time when a MPU starts its operation or a machine cycle. Okay, now if the microprocessor is presently in fetch mode, then it is fetching the operational codes from the memory. So basically 8085 takes 4 T states, and during the first T state of that particular machine cycle, all the buses, that the address bus, upper address bus and the lower address bus, will be used as address bus, which will generate a 16-bit address. But after that, the lower order address bus can be used as data bus, which can be used to get information from memory to the microprocessor, or from the memory to the or from microprocessor to memory or IO. Well, let's see what are the other control signals and status signals. Read control signal is active low type. It is used to retrieve or read data from IO or memory. Similarly, write, this is a write control signal. It is again active low. It is used to write data from MPU to IO, that is input output system, or the memory. We have to remember one thing: the microprocessor can do one thing at a time. That is, if presently the microprocessor 8085 is in the read mode, the write terminal will be inactive, and if it is in the write mode, the read terminal would be inactive. Well, IO M-bar, this is a terminal. It is a status terminal which is used to differentiate between the operation that is the microprocessor is currently in. Now when the microprocessor is communicating with memory, IO M-bar terminal will be low, and if it is communicating with the input output device, the IO terminal will be high. Now we can see the control signals and the status signals together. S1 and S0 are again two status signals when are used along with IO, which indicates the various operations of microprocessor 8085. Now on the left hand side we can see the machine cycle types. We have the status signals, we have the control signals. Now when the microprocessor is in the opcode fetch mode, obviously it is the opcode or the operational code is available in the memory, so it will be working with memory, hence this particular terminal is low. And if it is, and since it has to be read from the memory, both these terminals will be high, and the control signal that will be generated is read. Now if the microprocessor is in the memory read cycle, it is similar to opcode fetch cycle, that it is reading for the memory, except it is not a operational code fetch, it is any data fetch type of operation, hence it is again 0. But these two signals differ. 1 0 here means we are reading something from the memory. I mean the microprocessor is reading something from the memory. The memory write, this again has to be 0, and it is 0 1 here. We are writing something from the microprocessor to the memory. Please mind it, we are not writing anything to IO because this particular signal is 0. Hence the control signal write will be low. Now IO read, here the change comes. IO M-bar has now changed to 1, so the microprocessor is presently communicating with IO, and we can read something from that port. Any data that is available at the output port can be read using this, and this signifies 1 here and 10 here, signifies that we are reading. This and this are same, only difference is this 2, that is, if this is 1, this means IO read, and if this is 0 here, it means we are reading something from the memory. Similarly, IO write, this one will be 1 and 0 1. Again, we can see this and this is same, both are in the write operation, but the only difference is we are presently working with memory here, and we are presently working with memory here, and here we are working with IO. Now, if somehow interrupt has been generated, if someone has used the interrupt terminal, then these 3 will be 1 and INTA will go low, which will acknowledge that the interrupt has been accepted. Now, if the microprocessor presently in the halt state, then IO M-bar terminal will be in the high impedance state, and these two will remain 0. This means that the microprocessor is presently in the halt state. Now we can again see here RD and WR, that is the read and the write terminal, are both in the high impedance state. Okay, now in the hold state, now hold here, hold means if the presently microprocessor has to go into hold state for DMA operation, then the IO M-bar terminal will be in the high impedance state, and doesn't matter whatever there be in S1 and S0. During reset, the same thing happens. IO M-bar is in the high impedance state, and these two, whatever be it is, doesn't matter, means is in the reset state. Okay, now the power supply and the clock frequency. We all know it works on a single power supply, and it has to be 5 volts DC. The ground reference, that is the common potential, will be 0. Hence it is a single power supply. Now the crystal that is connected between X1 and X2 is 6 megahertz. When it is connected to the X1 X2 terminal, internally it is divided by 2, and the clock frequency turned out to be 3 megahertz. Okay, now the clock out. This signal is used as a system clock for the other devices. We may have certain sequential circuits which can be connected with the microprocessor to make those devices work in unison with the microprocessor 80885. We need a reference clock out, reference clock signal. Hence the clock out from the microprocessor 8085 is basically used to synchronize the other devices. Okay, now let's see the interrupt. INTR is the interrupt request. This is generally used to interrupt the microprocessor. Now in previously microprocessors were used to scan the IO ports for the availability of the data. It was a wastage of microprocessor's precious time. So in order to save the microprocessor's precious time, interrupt driven data transfer scheme was introduced, where if a data is available at any port of the input output devices, it will first request the microprocessor by sending a signal through INTR. The microprocessor will temporarily suspend its present work and acknowledge the interrupt and do the necessary work for it, and again get back to its original work. Now whenever an INTR is requested and the microprocessor suspends its own work and ready to work for it, INTA is generated, that is the interrupt acknowledgement. There are other restart interrupts, also known as RST 7.5, RST 6.5 and RST 5.5. These are actually vectored interrupts that transfer the program control to a specific memory locations. they have high priorities than INTR. Among these, the priorities are 7.5 is having the highest priority compared to 6.5 and 5.5. We will be discussing elaborately about software interrupts, hardware interrupts in our later lectures. There is another restart interrupt known as trap. It is also known as RST 4.5. This is a non-maskable interrupt and has the highest priority among the above, and it is only used during emergency situation. Okay, now hold. This signal indicates that a peripheral such as a DMA controller is requesting the use of address and data bus. Now, why should we at all go for direct memory access? Sometimes a bulk amount of data needs to be transferred from memory to IO or vice versa. When we are transferring bulk amount of data, it sometimes doesn't require any computation to be done on it. It just requires simple transfer from IO to memory or memory to IO. So if it goes through the microprocessor, then it will take a huge amount of time. So to bypass the microprocessor, what we need to do is we need to have a DMA controller, that is direct memory access controller, which will generate a signal, a hold signal for the microprocessor. The microprocessor will then acknowledge the hold and tri-state the buses, the address and data buses. If the address and data buses are tri-stated from the MPU point of view, then IO and memory can gain the control and initiate the transfer process among themselves. Okay, the next one is ready. Now sometimes very slow devices are connected to microprocessors. So the microprocessor is a very fast device, so if a slow device is connected, then the transfer between the data transfer between the microprocessor and the slow device can be a problem. So the signal is used to delay the microprocessor's read and write cycle until a slow responding peripheral is ready to send or accept data. So a slow peripheral can use this ready terminal to deliberately slow down the microprocessor so that the read and write cycle happens properly. Well, the next thing is reset in. Now we all know the microprocessor is constructed out of combination and sequential circuits, and sequential circuits are more often constructed out of sequential circuits like flip-flops, registers are all working on clock. Now a simple program counter, which is a register type, is nothing but constructed out of flip-flops. Now whenever you first time switch on the flip-flop, it is extremely difficult to predict the output of it. The output may be set, the output may be reset. So imagine we have a program counter which is basically used to point to the location from where the microprocessor will fetch the operational code, but when it is first time switched on, we will never know what will be the content of PC, that is the program counter. So in order to start the device from a predefined location, we need to reset all the flip-flops of the program counter. So in a microprocessor we have a power on reset circuit which will actually set the program counter to 0 so that it can start from a predefined location. Now reset out. The reset out is a signal. Reset out is a signal that the MPU is being, which actually indicates that the microprocessor 8085 is reset in the reset condition. There are many devices which are being connected with the 8085, and if the microprocessor in the reset condition, the other devices also need to know that the microprocessor is presently in the reset condition. So reset out sends out the signals which indicate that the particular microprocessor is in the reset condition. There are two pins used to serially transfer data into the system and serially transfer data out of the system. Those are called serial input data and serial output data, are designated as SID and SOD. We will discuss serial input data and serial output data when we will take up the lecture on interrupts. Thank you for watching this presentation. Have a very nice day. Bye bye.